Dear students, in this particular lecture, we are going to discuss about theory of probability. In this series of lectures, we will first introduce you to theory of probability and subsequently we will move to the next level of syllabus. In today's lecture, we will just discuss preliminary things about theory of probability, the preliminary things which will be useful for you to learn probability in a better way. We request you to see the video completely to understand the things in a better way. So here we go. First of all, what is probability or what is probability theory? Probability can be defined as the science that deals with uncertainties and helps us to take decisions about actions even in the midst of uncertainties. So probability is a funny science. In probability, it you deal with uncertainty, still probability helps us to take decisions about actions even in between uncertainties. Probability theory actually originated in the games of chance. Gamblers they used to apply probability in their games to find out the most probable bet in that cases. Actually, the probability theory was born in France by two mathematicians, Blaise Pascal and Pierre de Fermat. Blaise Pascal, we know Pascal's law. So one day, one gambler came to Pascal and requested him to solve a problem of a dice game. Blaise Pascal, in return, started thinking and he wrote to Pierre Fermat. And between these two people, the correspondence led to introduction or the preliminary part of development of theory of probability. Thereafter, many people continued the research and the research starting from 17th century, that is the time of Pierre Fermat and Blaise Pascal, after 300 years has developed into a full-fledged theory. So now where are the applications of probability? So applications of probability, as I already told you, that it was used by gamblers to simplify complexities of betting games. But now it has been used in various processes, decision-making processes by business firms, government, professional and non-professional organizations. Probability is extensively used in economic decision making, business forecasting. You might have seen weather forecasting coming out, and in an interesting way, the win predictor in IPL matches, which you see, that is also the algorithm which is designed to predict that win is based on probability theory. So, where is the application in physics? Yes, we have application of probability theory in physics. We have already studied such applications. For example, we have studied the application in the thermodynamics. For example, Maxwell's law of velocity distribution, which is based entirely on probabilistic velocity distributions of molecule. So there we have quantum mechanics in physics, which is probabilistic in nature. In quantum mechanics, you can only tell probabilistic results. You can never tell the exact result. So let us start. First of all, we will like to introduce you to random experiment. So what is a random experiment? It is different from the experiments which you perform in your laboratory. The experiments which you perform in your laboratory, they have a definite result, and if even you repeat them under identical conditions, you are expected to get similar results. May not be exact same, but similar result. For example, consider the experiment of measuring acceleration due to gravity by using a bar pendulum. If you take the bar pendulum to another laboratory with the same stand, then you are expected to get a similar result, the value of acceleration due to gravity in that experiment. But random experiments, they differ. What is a random experiment? So the random experiment, if you conduct it repeatedly under homogeneous conditions, means identical conditions, then it will not give you same result. It will give you a different result. And the funny thing is that you know all possible outcomes also. All possible outcomes, results are already known to you. But you cannot say which is the exact results that will be coming in your experiment. So what is a random experiment? An experiment whose outcome is known, but you cannot tell with certainty which outcome will come. For example, when you toss a coin, you get either a head or a tail. So here there are two possibilities, out of which any one of the outcomes may occur, either head or tail, but you cannot say which one would be. Whether it is head or tail, you just cannot say. So that is a random experiment. An experiment, if conducted repeatedly under homogeneous conditions, they don't give the same result, although the result is known to you. Other example will be throwing a die. Here also, 1, 2, 3, 4, 5, 6 are the outcomes which are expected to come, but you can't say which one would arrive. Now, what is trial and event? So when you perform a random experiment like tossing of a coin, this is called trial, and the result which you obtain in the random experiment, that is called event. So very simply, tossing of a coin, you can call it a trial, and getting either head or tail, you can call that one as an event. Now the events may be simple or elementary. So how? For example, there will be events where a single possible outcome of the trial is there. So otherwise, if there are multiple possibilities are there, then it is a composite event. So what criteria determines an event, whether it is simple or composite? So for example, again we take, if you throw a die, then the event of getting 5 is a simple event, but the event of getting an odd number is a composite event, because the odd number can be 1, 3 as well as 5. There are 3 possibilities of getting 1, 3 and 5, and the event of getting odd number therefore is a composite event. But while throwing a die, the event of getting 5 is a simple event, because it has a single possible outcome. Then you will learn about exhaustive events or cases. So the collection of all possible outcomes of a random experiment is called exhaustive cases or exhaustive events. If you toss a single coin, then you get either head or a tail. So there are 2 exhaustive cases. If 2 coins are tossed, then the exhaustive cases will be how much? Definitely 2 square, that will be 4. If you throw 1 dice, then there are 6 possible cases. But when you throw 2 dice together, then the exhaustive cases will be 6 square, which is really 36. So now favorable cases. The number of outcomes of a random experiment which result in the happening of a desired event are called favorable cases of the event. So when you perform a random experiment, then the outcomes of the random experiment which result in the happening of your desired event, they are known as favorable cases. So let us again take an example. In throwing a die, the cases favorable for the event of getting an even number is 3, and they are 2, 4 and 6, because out of the 6 possible outcomes, 1, 2, 3, 4, 5 and 6, the 2, 4, 6 are the events which give you an even number. So in throwing a die, the cases favorable to the event of getting an even number is 3. For example, when you draw a card from a full pack of 52 cards, the cases favorable to getting an spade is 13, and that of getting an ace is 4, and a king of diamond is 1. I am going to tell you about the composition of cards a little later in this lecture. For the time being, we proceed with this. So next thing that we are going to learn is mutually exclusive events or cases. So mutually exclusive event, as the name suggests, the word is excluded present here. So events are said to be mutually exclusive if happening of one prevents the occurrence of all the others. So if one of the event occurs, the other event does not occur. So mutually exclusive events are also known as disjoint events. For example, in tossing of a coin, head and tail are mutually exclusive events. That is, if head occurs, tails will not occur and vice versa. So that is very simple. If one event occurs and it prevents the happening of the other, then it is mutually exclusive event. Or in throwing of a die also, if the number 1 occurs, then 2, 3, 4, 5, 6, they won't occur in the throw. So they are also mutually exclusive events. Equally likely cases. The outcomes are said to be equally likely if there is no reason to prefer one event after the other. For example, while tossing of a coin, if the coin is unbiased, then all outcomes head and tail are equally probable. Similarly, if your die is unbiased, I mean there is no trick has been applied to the die, then if it is a fair die, then all 1, 2, 3, 4, 5, 6 are equally likely when the die is thrown. Now, independent event. What is independent event? Two events are said to be independent of each other if the occurrence or non-occurrence of one of them does not influence the occurrence or non-occurrence of the other. So it is very clear that the definition of independent event, that there is one event, there is another event, but they are no way linked with each other. For example, when you toss a coin and you throw a die, then these two are independent. The result of the toss is independent of the face value of the die. Again, for example, when you toss a coin 2 times, then the second result, that is the result obtained in the second throw, is no way linked with the first throw. Then those are examples of independent events. Next, what is simple point and simple space? A simple point is an ordinary, elementary event, and the set of all possible results, that is the outcomes of a random experiment, is called a sample space. For example, when we throw a die, we have the outcomes 1, 2, 3, 4, 5 and 6. Here there is a mistake, that 6 is not there, but the sample space is denoted by capital S, and 1, 2, 3, 4, 5, there should have been a 6 here. Okay, one more sample space I am going to show you. For example, when you take 2 coins and toss them simultaneously, then the outcomes are either head head, tail tail, head tail and tail head. So these are the examples of sample space. So going back to the main slide again. So we have defined sample point and sample space also. Now what is complementary event? So what is in complementary event? Two events, capital A and B, are said to be complementary to each other if the event B represents the non-occurrence of the event A. So the symbol of the event complementary to event A. If A is the main event, then the complementary event is AC or A dash uh, or A dash. So if the event B represents non-occurrence of event A, then it is AC. For example, if you call A is the event of getting a multiple of 3 when a die is rolled, then we have A is 3, 6 and A complementary is 1, 2, 4, 5 because 1, 2, 4, 5 are not multiple of 3. So A is the main event and A dash is the complementary event. If you take this one as your main event, then this can be taken as the complementary event also. Then union of two events. The union of two events, generally denoted by A union B, represents those sample points which belong to either A or B or both. So this is very important because in the next lecture you will need this concept. So union, remember, it means either, I would like to highlight this, either A or to B or both. And the union may be extended to any number of events. And in intersection of two events, two events, you have this symbol and they belong to both A and B. That is, the events which belong to both A and B, they will be taken, but here A or B or both. So this union of two events and the intersection of two events, they are actually governed by the set theory. So now let us move on to another thing called conditional probability. What is conditional probability? Sometimes it happens that the probability of an event depends on the occurrence or non-occurrence of another event. So let us take a simple example, that is to illustrate further the dependence of one event on another. So suppose a person carries an umbrella. So probability of a person carrying an umbrella is high if the day is cloudy or rainy, and otherwise it is less. So if capital A is the event that the person carries an umbrella and capital B is the event that the day is cloudy, then the event A is dependent on B. That is, the event A that the person carries an umbrella is depend on how is the day, whether it is cloudy or whether it is rainy. So A given B, this vertical bar, A vertical bar, B vertical bar represents conditional probability. We'll explore conditional probability in next lectures, but here the A given B is the event that the man carries an umbrella when it is known that the day is cloudy. That is, the man is carrying the umbrella provided the day is cloudy. Sometimes it may happen that A, the event A, will not depend on B. Then simply A given B, the event, is simply the ordinary event E. So we'll explore conditional probability more in next lecture. So now coming to the main part of the definition of probability. So what is the definition of mathematical definition of probability? So probability is simply classical or mathematical definition: favorable number of cases and exhaustive number of cases. That is, out of your sample space you have to pick out which are the cases favorable for your event and what is the total number of events. That is, it is m by n. So it is very simple. Probability of an event is favorable number of cases divided by total number of cases. Now, what are the properties of probability? Probability of an event lies between 0 and 1. That is, if capital A is an event, then the probability always lies between 0 and 1. Probability of an impossible event is 0. Impossible event means the favorable number of cases is 0, so probability is 0. Probability of a certain event is equal to 1. When favorable cases and exhaustive total cases is same, then the event is certain. If the occurrence of an event A implies occurrence of another event B, then probability of A less than equal to B. That is also there. Probability of happening of a particular event and the probability of non-happening of this event, when added, they give you unity. That is, probability of A plus probability of A bar is 1. That is also a very important result in probability theory. That is, your probability of A and probability of A bar, that is the non-happening of the event, that this is non-happening of the event, probability of non-happening of the event, this is your probability of happening of the event. So they together makes us 1. So that is also an important thing in probability theory. So this is some of the preliminary things that we have discussed here in this slide. So I will move to the next slide and tell you something that I told you earlier. That is, I told you that we will introduce you to the combination of pack of cards. So you have 52 cards in a deck and they consist of 4 suites: diamond, club, hearts and spade. So this is your diamond 1. Then you have this suite, diamond is red in color. Then you have that club suite which is black in color. Then the next one is your heart, you have the symbol of heart here, this one. Then you have spades, this one. So each suite, we have total 52 cards. Each suite carries 13 cards. 13 cards are A, which is called ace, and then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are 10 ace cards, they are called. And we have 3 picture cards. The picture cards are jack, queen and king, J, Q and K. And similar pattern exists in the other suites also. So to recapitulate, what we learned in today's lecture is that we discussed how probability theory originated. Then we discussed basic terminologies like random experiment, trial and event, exhaustive events or cases, favorable cases, mutually exclusive events or cases, equally likely cases, independent events, sample point and sample space, complementary event, union of two events, intersection of two events, conditional probability, mathematical definition of probability, and we also introduced you to pack of different pack of cards, 52 cards, and their introduction also were provided. So with this, we wind up this lecture. Next lecture, we will go to the main part of our syllabus. There we will start with the definition of mutually exclusive events and the different mathematical results of probability theory. Thank you.